Hello everyone, I'm Sujay Narayana from TU Delft. Our work on an isolated satellite health monitoring system is a collaborative work between TU Delft and Indian Institute of Science. In the recent years, the rate of launch of satellites has grown significantly. Alongside successful launch missions, the failure rate of satellites has also surged. According to NASA, 35.2% of the satellites launched since 2000 have failed completely. When the satellites fail before their expected mission time, the financial loss incurred is substantial. For instance, Boeing faced a loss of more than 400 million US dollar when Intelsat 29E failed in the orbit. Similarly, Russia lost a 256 million US dollar satellite due to communication issues. Likewise, 5% of these Starlink satellites failed after their launch in 2019. So, when we say a satellite can fail, let us see the major subsystems of a satellite and what can fail there. This is our own Delphi Next nano satellite that was launched in 2013. Different subsystems are stacked one above the other as shown here. This is the power subsystem responsible for power monitoring and regulation. This is communication subsystem using which the satellite communicates with the ground station. Next, onboard computer, the main processing unit, and attitude determination and control system that is responsible for changing the attitude of the satellite. The health status of these subsystems are transmitted to ground stations regularly via its communication subsystem. When a module malfunctions, then the information received on the ground station can be analyzed and then appropriate commands can be sent to the satellite to revive it. For instance, in 2018, Hubble telescope's gyroscope failed. Then the redundant gyroscope was activated and even that was not functional. Finally, the satellite was revived by sending a reboot command from the ground station. So, if you know the cause of failure, then it may be possible to fix the error and revive the satellite. Considering failure of a subsystem, let us say the power system is dead, then the satellite is completely dead and the reason for failure is not known. Similarly, if the communication subsystem fails, then there is a complete communication blackout and we will not know the cause of the failure. Same with the thermal system. Further, a failure in one subsystem may cause the failure of the other. Hence, it is very important to know the failures of a satellite in orbit, not only to check the possibility of reviving it by sending commands, but also such failures can be avoided in the future satellites. Well, fault monitoring systems are not new. There are ample works in the literature for supervising the critical systems for failures. A widely accepted method is software based. If there is no communication with the specific subsystem, then we can declare it as a failure. Apart from software, another most common approach to fault detection is hardware redundancy. However, this scheme failed even in the case of Hubble. Ground-based fault-tolerant systems include data analytics that employ the historical data received from the satellite. This is a time-consuming process and may not be beneficial if we need to telecommand the satellite immediately. Another solution for health monitoring in satellites is to have a separate hardware module that monitors different subsystems regularly. However, this is electrically connected to the satellite and relies on satellite's communication system for data transfer. Any failure in the main satellite power system affects this health monitoring module. To this end, we present a simple, completely independent, isolated, and miniaturized module called Chirper that can provide a secondary channel for the health monitoring system of satellites. Chirper can track the satellite health parameters at regular intervals and then transmit them to the ground station independently. It can monitor important parameters of a satellite such as the tumbling rate, its attitude, communication status, temperature at different locations, and more importantly, it can measure the DC voltage and current on different power lines in an isolated way. These parameters are transmitted by the Chirper to ground stations using its own LoRa or FSK based communication channel at regular intervals. If there are any failures in the satellite, further action can be taken by the satellite manufacturers to save the satellite. Chirper consists of three main units: energy harvesting and power management, data processing and sensor unit, and communication unit. The system is powered by 6 tiny solar cells. A supercapacitor is used as an energy bank that powers up the chirper when it is on the anti-sun side of the Earth. A space-qualified MSP430 microcontroller is used to process the data. An inertial motion unit comprising of accelerometer, gyroscope, and magnetometer provides the tumbling rate of the satellite as well as its attitude. So, if the ADCS system of the satellite fails, then we can know the attitude of the satellite from this IMU. Multiple thermistors placed at different locations on the satellite provide thermal information to the chirper. More importantly, chirper can measure the DC voltage and current at different points of interest. All the information gathered is transmitted to the ground station on its own communication channel that employs LoRa or FSK, and these are duty cycled. Let us say every 30 seconds there will be one transmission. The overall power consumption of chirper is around 250 milliwatt when the data is transmitted at 22 dBm power. While the chirper can be powered using just a single solar cell, we explain why 6 cells are needed. Let us consider a scenario where 5 solar cells are mounted on each side of a cuboid satellite. Assuming that the satellite is not tumbling, there may be a case where the side without solar cell is pointing towards the sun continuously. Even if the satellite is tumbling in the direction indicated by yellow arrow here in the image, sun rays are not incident on any of the 5 solar cells. This gets worse as the number of cells decreases. Let us consider another scenario where solar cells are deployable as shown here. The tumbling direction is marked by the yellow arrow. Even in this case, the solar cells of the chirper are not illuminated irrespective of whether the satellite is functional or not. Hence, if all the sides are mounted with at least one solar cell on each side, chirper will always be powered. In these videos, you can see how the satellites rotate in orbit, especially when they are not equipped with attitude correction systems. 6 solar cells ensure that the chirper is powered on all the times and can monitor the satellite continuously. Now, to measure the low DC voltage in an isolated way, we have a few design choices. First one is using isolated DC-DC converters. Here, the isolation is based on transformers or LED photodiodes. This system is not only bulky, but also requires one part of the system to be electrically connected to the parent satellite. Any electrical short in the system can shut down the entire satellite. Another way is to use surface potential sensors to measure DC voltage on the surface of a conductor. However, these sensors are expensive and intended for detecting high DC voltages with a measurement resolution of around 10 volt. This is not sufficient to measure the DC bus voltage of a satellite that can vary between 0 to 48 volts. At least a resolution of 1 volt is necessary here. There are a few works in the literature where coupling capacitance formed between the conducting wire and its insulation is measured to estimate the voltage. However, this technique is widely used for AC voltage measurements or to detect only the presence of high DC voltage. The unavailability of an isolated low voltage DC measurement method motivated us to develop a new technique. Let me explain this in a simple way. Let us consider two capacitors C1 and C2 with different dielectric mediums, and they are connected in series as shown here. The potential of V is applied between terminals X and S. Let terminal E be a tap from the junction point of the capacitors. If a potential V0 such that V0 is less than V is applied on terminal E, then the charge stored across C1 and C2 varies proportionally to V0. Now, by measuring the charging and discharging time of C1, we can estimate V0. Further, the dielectric medium of C2 is replaced by vacuum and plates Q and R are merged to form plate Y. Plate X is connected to a DC power supply V through a resistor R. The charging and discharging of the capacitor is controlled by the microcontroller using two MOSFETs as shown in the image here in the right. A non-conductive dielectric medium is sandwiched between plates X and Y. Since there is no electrical contact between plate X and Y, the chirper and the voltage line to be measured are isolated completely. The capacitance formed between X and Y will be very small, in the order of picofarads, and this results in charging and discharging time in the order of nanoseconds. This is not easy to be measured using a 16 MHz microcontroller. Hence, by increasing the input voltage, let us say up to 90 volts, and dielectric constant of the capacitor, let us say up to 80, the charge and discharge time can be increased. The isolated DC current measurement is straightforward. We adopt the existing non-intrusive method of estimating the current flow in the current carrying wire. We use a Hall effect sensor placed in the air gap of a flux concentrator. The Hall effect sensor provides voltage output proportional to the magnetic flux created around it due to the current flow. This method provides complete galvanic isolation. We evaluated the performance of chirper in different scenarios. First, the proposed DC voltage measurement technique was validated with simulation as well as real-time voltage measurements. This is one of the simulation results with V0 equal to 48 volt and V equal to 90 volt. We obtained the measurement accuracy of 0.007 volt with simulations. Next, the entire chirper was mounted on a test system which had a cube and one solar cell on each side of the cube. The chirper was placed inside the cube and mounted on a 3-axis rotation mechanism. This was subjected to the solar simulator to test the amount of energy harvested. An example of a solar simulator and the rotation system is shown here. These are not the actual ones, but we have restrictions on posting the actual images here. The experiments shows that irrespective of the tumbling direction or speed, the chirper could harvest at least 145 milliwatt of power that almost matches with our solar power model calculations. The chirper was also mounted on a real satellite and tested extensively. Multiple voltage and current measurement probes were connected across different subsystems of the satellite. The images on the right shows our experimental voltage and current measurement probes. Here is the result of our proposed approach for measuring DC voltage. We observe that 90% of the time the error is within 0.8 volt and the maximum error observed was 0.9 volt. For current measurement, the maximum error observed was 62 milliampere. The chirper was launched on a helium balloon up to 2 km altitude from the ground station receiver to emulate the tumbling scenario and also validate the communication range. We used just one solar cell. The data was transmitted on both LoRa and FSK alternatively every 5 seconds. The voltage generated by the solar cell at different tumbling rates for 200 minutes of flight is shown here. As there was no attitude control on the balloon, the tumbling rate was very high as 146 degrees per second. However, in an actual satellite, the tumbling rate will be much less than this. Thus, this experiment depicted the occurrence of the worst case scenario. This experiment also validated that the chirper can be functional even with a single solar cell. The RSSI obtained at different distances for both LoRa and FSK is shown here. Though the distance between the ground station receiver and the balloon went up to 2 km, we extrapolated the results up to 2000 km to emulate it for satellites. The results showed that it is possible to decode the messages successfully if the transmission is with LoRa SF7 and at 125 kHz bandwidth. Further, it is shown that at the same transmission power, LoRa outperforms FSK over distance. This is also evident from the graph. However, the selection of physical layer, spreading factor, transmission bandwidth, and antenna gains are up to the satellite manufacturer. To conclude, we presented a novel and complete design of a low power and independent satellite health monitoring system called Chirper. We also provided a new approach to measure the DC voltage in a complete isolated way. We are the first to provide such an isolated voltage measurement solution, and this technique can be used not only in the space domain but also in terrestrial applications. Chirper is flexible to be mounted anywhere inside or on the body of the satellites, almost of any size. Now, with all the space launch related requirements fulfilled, it is expected that Chirper will be on board a space system in a few months. While Chirper is designed only to detect faults and monitor the satellite, it cannot fix the problem on the satellite on its own. However, the data received from it can aid in reviving failed satellites. Thank you.